hopefully you worked on simplifying these expressions a little bit, because they do turn out to be really, really nice. Alright, so let's just work with one of them at a time. This first one. If we write this out, we would have 2u1 dotted with au1 plus bu2 minus v3. And writing this out, I'm just going to keep the 2 in front because who really cares about the 2. Dotting these one at a time, right? You want to distribute them in. You're going to have a u1 dot u1 plus b u1 dot u2 minus u1 dot v3. And there's one very, very nice thing that happens in here. In particular, what was the whole point of what we've been doing here? It was to guarantee that u1 and u2 are orthogonal to one another. That was the first 2 steps of what we did in this whole procedure. And so this term right here, u1 dot b times u1 dot u2, is gone. That's 0. And so what we end up with is 2a times u1 dot u1 minus u1 dot v3. And the 2 is in front of everything. You would get the same thing if you did the second line of this, except the a u1 dot u2 would vanish, and you'd be left with b u2 dot u2 minus u2 dot v3. All right, same idea. So, all told, we are trying to minimize this function, f. Right, I called it f up here just for simplicity. We want to minimize this thing. So to minimize f, we want to solve gradient of f equal to 0. So, setting these 2 equations equal to 0, right, the 2 components of the gradient, that is, which we just simplified a little bit, gives us the following. The first one says that a u1 dot u1 should be equal to u1 dot v3, and the second one says that b u2 dot u2 should be equal to u2 dot v3. And remember, the values of a and b are really the things that we care about from this. So we can solve this for a and b, and we would get the following. A should be u1 dot v3 over u1 dot u1, and b should be u2 dot v3 over u2 dot u2. Okay, so let's summarize this, because we don't have everything from the previous video right in front of us. So let's summarize this. Just to remind you what a and b represented here. The projection into this plane that's spanned by u1 and u2, we're trying to figure out the point that's nearest to v3 in that plane, because this is going to be the end point of the projection of v3 down into the plane that's spanned by u1 and u2. All right, so the idea here was to minimize the distance from the plane to this vector v3, and what we've just found is that the point in the plane spanned by u1 and u2, which I was calling S in the previous video, the point in S, which is nearest v3, is a u1 plus b u2, where a and b have these formulas. So if we write this out, this is going to be u1 dot v3 over u1 dot u1 in the direction of u1. That's a u1 plus u2 dot v3 over u2 dot u2 in the direction of u2. That's b times u2. And now these things, right, this is so cool I can't even stand it. These things we have seen many, many times. What we've got here is the projection onto U1 of V3 and the projection onto U2 of V3. Right, these things are just projection formulas, which is really, really cool. So the idea here is that if you've got this picture of a plane again with U1 and U2 in it, so let me just bring that back. And in this picture, we've got U1 and U2, which are down here. They're already orthogonal to one another because of the procedure we did to them. And this blue vector is this projection vector, which we just calculated in light blue above. This is the end point of this light blue vector is the nearest point from V3 to the plane, right? So this is what we've been trying to calculate this whole time. And the purple vector is what we're ultimately after, right? We're ultimately after the part of V3 that's orthogonal to both U1 and U2, meaning orthogonal to the plane spanned by U1 and U2. All right, so that's just a 30-second recap of everything we built up to in the last video. And what we've just found in this is that projecting down onto this plane spanned by U1 and U2 is actually the same thing as projecting onto U1, projecting V3 onto U1, and projecting V3 onto U2, and then adding those two projections together to turn them into this blue vector in the middle. All right, so this is really the idea. We would have this instead, and so this would be, right, if I draw this green vector here, this would be the projection onto U2 of V3, and this green vector just sort of moved down the line a little bit, and obviously I didn't draw this perfectly because those vectors aren't really the right size, but hopefully you get the idea. This vector right here would be the projection onto U1 of V3 just moved over a little bit, sort of transplanted. And so adding these two things together gets you to the right spot, which is this nearest point, the tip of the shadow of V3 when the light casts the shadow onto the plane. All right, and this works out so incredibly beautifully because we made sure U1 and U2 are already orthogonal. That is why these formulas, right here, that's why these formulas work out so very, very nicely, where U1 and U2 dot to 0, because we already ensured that those were orthogonal to one another. All right. If they aren't already orthogonal, this same really beautiful formula doesn't work exactly the same way. You have to do a little bit more work because those terms in the dot products above wouldn't just zero out for you. All right, and again, this is what I was calling S. That's that plane spanned by U1 and U2. Okay, so this is the idea. If you want to figure out the projection of a vector onto a plane that's spanned by two orthogonal vectors, U1 and U2, it's enough to just calculate the orthogonal projection onto each one independently and then add them together. All right, and this tells us exactly how to calculate this purple vector, which is what we actually wanted from all of this. This purple vector is what we're going to call U3. That's going to be our third vector in our new orthogonal basis. All right, so summarizing this, we start with, just to remind you of how all of this is working, we start with V1, V2, V3, which are not necessarily orthogonal, and we want an orthogonal basis U1, U2, U3. And we start off by, so we start with a non-orthogonal basis, V1, V2, V3. We want to generate an orthogonal basis, U1, U2, U3. All right, so we let U1 be V1, let U2 be V2 minus its projection onto U1. If you want to write this out in more detail, this, of course, is U1 dotted with v2 over u1 dot u1 in the direction of u1. And u3 now is going to be v3 minus the projection onto the span of u1 and u2, which is that plane, that I was calling S for brevity, of v3 itself. And if you want more detail in this formula, this is v3 minus u1 dot v3 over u1 dot u1 in the direction of u1 minus u2 dot v3 over u2 dot u2 in the direction of u2. All right. In other words, this is, if you write it out even in a slightly different way, this is v3 minus the projection onto u1 of v3 minus the projection onto u2 of v3. All right, so a few different ways of writing the exact same thing. Okay, now, I want to talk about coherence for a second, right? Because I mentioned this idea of generating an orthogonal basis from the original that is somehow sort of faithful to the original. It's somehow coherent with the original information. So let's just talk briefly about that. And to do this, I want to use these sort of more specific formulas rather than the projections. I want to use the more specific formulas to build our intuition. All right, so first things first. With u1, that just is v1. So, since we've done nothing to it, this is sort of a silly thing to point out, but it is still true, and I do want to make a point of it. The span of u1 is exactly the same as the span of u2. And this is trivial because they are identical. Right? u1 is u2. So I'm just saying the same thing over again here. I'm not really saying anything. Now, the more slightly complicated part. The span of u1 and u2 together. Well, if we look at the formula for u2, it's got v2 in it, and it's got u1 in it. But remember, u1 is just v1. All right, so u2 is a linear combination of v1 and v2. All right, so we used both v1 and v2 to generate u2. So this means that if I take linear combinations of u1 and u2, it's the same thing as taking linear combinations of both v1 and v2. All right, so this is the idea. The span of u1 and u2 turns out to be the same as the span of v1 and v2. And the idea of why this is true is that u1 and u2 are both just linear combinations of v1 and v2. So the set of all possible linear combinations of v1 and v2 will be the same as the set of all possible linear combinations of u1 and u2. All right, so this is what I mean when I said coherence before. This is the sense of coherence that we're generating. All right, we're not just scrapping the original basis, throwing it away, and starting from scratch with an orthogonal one. We are doing it in a way that is still faithful to the original basis, in this way. All right, this is how it's still faithful. And lastly, using this formula that I circled in blue here, we can see that u3 is a linear combination of v3, u1, and u2. But remember that u2 is a linear combination of v1 and v2. So this really tells us that v3, right, if I write it in green here, v3 is a linear combo of v1, because u1 is present, which is v1, v2, u2 is present, and u2 is a linear combo of both v1 and v2, so v2 is included, and v3 is right there. So this tells me that if I look at the span of u1, u2, and u3 all together, this is the same as the span of v1, v2, and v3 all together. Now, this last point I really didn't need to make because I'm assuming that these three vectors form a basis, which means that the dimension of the vector space that I'm talking about has to be 3, because it's got a basis with 3 things in it. And so the span of these 3 basis vectors is going to be the entire space. The span of these 3 basis vectors is going to be the entire space, and so of course they're equal. But if this were a dimension 4 space, doing this same procedure, I could still guarantee the same thing about these first 3 vectors. And this is what I'm going to do on the next page when we make this fully general. All right, so just to reiterate, this sense that I have sort of expanded on here, this is what I mean when I say that the new basis, the new orthogonal basis, is sort of coherent with the original. Right? This is what I meant when I said coherent. I wanted to build up a little bit more language before just dropping this bomb on you and having you struggle to figure out what that meant. All right. So this procedure has a name. It's extremely famous and extremely useful. So let's talk about that on the next slide. All right. The Gram-Schmidt algorithm is the name of this thing. It's extremely famous and extremely useful. Because of the last video, or rather 2 videos ago, I did define this idea, or at least talk about this idea of a general inner product. Basically, it's just a generalization of the dot product. And this Gram-Schmidt algorithm works on any inner product space. So I'm going to phrase it in the language of inner products. Just keep in mind that anytime I talk about an inner product of 2 things, you could replace it with a dot product, and it's exactly the same. All right, so after I state this thing, I'm going to talk about a couple results that follow from this, and then we are going to do some examples. All right, so if you're given an inner product space, call the space V, just so I can refer to it easily. And the inner product is given by this funny angled bracket notation. And you've got a basis already, V1 through Vn. Then the whole point of the Gram-Schmidt algorithm is to turn that thing into an orthogonal basis that's somehow coherent with the original. And it's via the following formulas. All right, so the algorithm itself is the formulas that I'm about to go through here. All right, U1, just set equal to V1. All right, that's easy. U2, take that to be V1. Oh, I'm sorry, not V1, V2, minus the projection onto U1 of V2. Or, if you like, this would be V2 minus, and here's where the first difference between everything I've said before and what I'm going to say now in the context of an inner product space is going to be a little bit different. This is going to be the inner product of U1 V2 over U1 inner product U1 in the direction of U1. All right, and again, this is identical to everything I've said before. I'm just replacing the dot product notation with the inner product notation. U3, we take to be V3 minus the projection onto the span of U1 and U2 of V3. And remember, we saw a little bit earlier that this is the same as V3 minus the projection onto U1 of V3 minus the projection onto U2 of V3. And again, if you want to see explicit formulas for this, you know how to calculate projections because we've done it 100 times now. This is U1 inner product V3 over U1 inner product U1 in the direction, in the direction of U1 minus U2 inner product V3 over U2 inner product U2 in the direction of U2. And now, this is how this really goes, right? You define your first vector right here. You use U1 to define U2, right? So they inform one another. And then you use U1 and U2 to define U3. And next you'll use U1, U2, U3, which you've already defined, to define U4, and so on and so forth. Right? This is going to continue inductively in this way, meaning you use all the stuff from the previous steps to create the next step until you create your last vector, which is going to be Un, and this is going to be original Vn minus the projection onto the span of all of the previous ones of Vn. In other words, this is Vn minus, and this projection onto the span of all these vectors, again, because we made sure that all of the u's, U1 through Un minus 1, these are all orthogonal by this procedure that we're doing. This projection, this giant projection onto a span of these vectors, turns out to be a sum of all of the individual projections. And this only works because we made sure everything's orthogonal up to this point. All right, so we can break this down into a sum of projections, right? Projected onto U1, projected onto U2, and so on. Projected onto Un minus 1, and subtract all those projections off of the original vector, and you get this new vector Un. And again, if you like the explicit formula version, this is U1 inner product Vn over U1 inner product U1 in the direction of U1 minus all the way up to Un minus 1 inner product Vn over Un minus 1 inner product Un minus, minus N minus 1 in the direction of Un minus 1. I apologize I ran out of space there, but hopefully you have the idea. And this is going to be your orthogonal set. All right, so some notes about this. First thing, the U's form an orthogonal basis. And it does so in a way, right, so it does so in a coherent way. Which I'll expand on here. It does so in a coherent way, meaning that the span of U1 is the same as the span of V1. The span of U1 and U2 together is the same as the span of V1 and V2 together. The span of U1, U2, U3 together is the same as the span of V1 v2, v3 together, and so on and so forth. All right, so all the way down the line until, eventually we're going to have the span of u1 through un minus 1 is the same as the span of v1 through vn minus 1, and the last one would be, of course, the span of all of them is the same as the span of all of the v's. All right, so this is what I mean when I say that they're coherent. You are changing the v's, right? You're creating the u's by changing the v's, adapting the v's in like the minimal possible way, just to make them orthogonal, but to still preserve all of the original information that's encoded in the v's themselves, at least as best as you can. All right, so this is what I mean when I say it's done in a coherent way. The third point I want to make about this, the third note, is that, again, if you want an orthonormal basis, you just have to do this Gram-Schmidt algorithm, and then when you're done, unitize. All right, so the idea is replace uj by uj divided by the magnitude of uj. All right, just give it unit length. And then you'll have an orthonormal basis instead of just an orthogonal one. So this algorithm is incredibly cool. It gives us two very immediate theorems, which are very, very nice to know are out there. And they're stated on the next page. All right, so there's a theorem here, which is that every inner product space has an orthogonal basis. And in fact, you can just very easily change that orthogonal basis by unitizing every vector to be an orthonormal basis. This is great because this tells you that no matter what inner product space you're working with, there will always be an orthogonal basis in it. It's just a matter of doing the work to find it. And I do want to make one small point here, which is that it's really not that important for this class, but this algorithm really only works if you're in finite dimensions. Not a huge point for this class. Now, a similar theorem does end up being true regardless of dimension, but you do have to be a lot more careful in how you say it. But I just want to point out that the Gram-Schmidt algorithm works because you've got a very clear beginning point, which is u1 and v1, and a very clear ending point, which is un and vn. If you had infinitely many of these vectors, well, you wouldn't be able to stop, really. So that's the only point I want to make about that. But the important thing here of this theorem is that you are always able to find orthogonal bases, and if you can find an orthogonal basis just by unitizing, you can find an orthonormal basis. And the proof of this theorem is Gram-Schmidt. That's the entire proof, right? Start with a basis. The fact that every vector space has a basis is not the hardest thing in the world to prove. And what Gram-Schmidt tells you is that as long as you've got any basis in front of you, you can always orthogonalize it. All right, you can always do this algorithm to turn it into an orthogonal basis if you want. So the proof is 100% Gram-Schmidt. All right, the next video, I want to show you some examples of why, number one, why I want to talk about general inner product spaces as opposed to just Rn with the dot product. And I'm going to do that by way of some examples.